Hey folks, Brian Jones here. This is our second set of slides, and this one is titled Review. And what I'm going to look at is some things that I'm expecting that you've seen before in previous courses that I just want to remind you of before we move on. But if you have questions about any of these topics, they're all covered in Chapter 1 in the textbook. So you can go ahead and take a look at Chapter 1, and that will help you review. But for most of you, this will just be a refresher of some things which you've seen previously. But before I do that, I want to talk to you personally a little bit. I want to talk to you about this, things I like about your generation. Now, for people of my age, it's fashionable to talk about how young people these days, they're so selfish, they're so self-absorbed, they don't care about this, blah, 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 they're lazy. I do not find this to be true. I find that young people these days, you folks are passionate, you're engaged, you're involved, you're worried about the world, but who wouldn't be at this particular moment? I think you folks are delightful. I think this particular generation of students is one I like so much. I like your particular generation so much. And I'm going to tell you some of the things I like about your generation. And one thing that I just love to pieces about you folks is your inclusivity. You are incredibly inclusive. And I see people being reflexively inclusive of people regardless of race and ethnicity and gender identity and anything I can think of. I see people being relentlessly inclusive in a way that I have never seen before. And you take this as a given, and it gives me heart and it gives me hope. So thank you. I will tell you regularly things I love about your generation because I like you folks so much. And I think you need to hear that. Now I want to talk about some material, and as I said before, this is material from Chapter 1 in the textbook. Chapters always start out with kind of an overview of what we're talking about. In this chapter, it says it's about representing motion, but really it's kind of like reminding you about some things that you already know. You know things about units. You already know things about describing motion. Okay, so this is material which you've likely seen before, but it sets up the topics to come. Now, the first topic I want to look at is this topic of significant figures, okay? And in the book, there are these little pictures like this one right here and a little text with it. We call these freestanding applications, or FSAs. And I want you to look at the FSAs, like if you're going through the chapter, and I would encourage you to take a look at these things because these are little pictures with some anecdotes that are designed to kind of like bring the topics to life. And often that means literally because we're taking those topics and we're applying them to the living world. So in this question asks this is a guy named Walter Davis, and he did a long jump, and his best jump was reported as 8.24 meters. Okay, now if you're claiming 3 significant figure accuracy on this jump, that means that you're implying that the actual jump was between this number and that number. That means you would be accurately knowing the length of the jump to an accuracy of 1 centimeter. And does that seem reasonable? That seems like a bit of a stretch to me. Although, maybe they put the tape out there and are very accurate and they measure the exact kind of like first spot where the sand is disturbed. So maybe. But we just want you to think about that. When you report a number, you always report a number of significant figures, and that tells you something about how accurately you know that number. Okay? And so we expect you to use the appropriate number of significant figures. And in this class, the default is 2. So if I'm giving the length of a long jump, I'm going to give it as 8.2 meters. And that means it's somewhere between 8.15 and 8.25. That's a span between here and here of 10 centimeters. Well, 10 centimeters is about 4 inches. And that seems reasonable. That seems reasonable to specify something to that accuracy. And that's going to be the typical thing in this course, is that we're going to have 2 significant figure accuracy. And it's usually a stretch to claim that you have accuracy more than that. Now, we want to talk as well about units, and this is something you're familiar with. In physics and other sciences, we use the so-called SI system of units, the Système International. That's meters, that's kilograms, and seconds, and associated units. Whereas you've been raised likely using the British or system of units, where we have like feet, and we have pounds, and we have seconds. But these units are kind of ridiculous. They're a lot harder to work with when you're doing science, so we're going to be using these ones right here. And it's going to be important to be able to convert between these units and have some sense of scale in these units, because we always want you, when you give an answer to a number, to think about it and see, does it make any sense? And there's a little freestanding application in the textbook about the importance of units. And this was a $125 million spacecraft that was lost because the team providing data on the spacecraft performance gave English units, but the navigation team assumed they were in metric. So because one team of people was using feet and one team of people was using meters, they piloted the spacecraft wrong and destroyed it before it could collect any data. And that's just an extreme case, but there's a lot of smaller cases. Know which units you're using, and in this course, the units that we're using are these SI units, meters, kilograms, and seconds. When you get final answers in this class, we always want you to take a look at them and see if they make any sense. We're going to ask you to do an assessment. And an assessment is you're going to look back at your answer and say, does that make sense in terms of what you know about the world? So for instance, suppose you're calculating the running speed of a gazelle and you come up with an answer that's 15 meters per second. Well, is that reasonable? Well, it turns out 1 meter per second is about 2 miles per hour. So 15 meters per second is approximately 30 miles per hour. And gazelles are pretty speedy, so that seems like a reasonable value to get. And so there's a table in the textbook of these approximate conversions. And you can use these when you're taking a look at final answers, which of course will be in SI units. And you're going to think, do they make sense in terms of your understanding of the world, which is quite possibly in the English units. One of the things you're going to learn about physics is that a lot of times we make simplifications to the world, and we just want to get kind of a ballpark estimate of how certain things work. And one thing we do is we do a lot of estimation, and we're going to ask you to do this particularly when you're assessing your final results. Just say like, estimate how fast something is moving, estimate how tall something is, etc., etc. So I want to remind you of this basic idea. So here's an example, and this is from chapter 1. If you were to estimate the average speed in meters per second with which the hair on your head grows, I mean, how would you do that? How would you do that? I want you to give, and then you're given some suggestions as to how you would do it. You could say, I know how often I cut my hair and how much I trim every time I cut it. And so you can get an answer that way. So let's take a look at that. I'll do a quick calculation to show you how you do it. Now it's complicated for me because I decided a couple of years ago I was like not going to cut my hair and just see how long it gets, and it seems to have kind of stabilized. Like the hairs grow so long and then they fall out and others take their place, and it doesn't seem to be getting any longer. So it's been a while since I've cut my hair, but back when I used to, I have this vague recollection that I would cut my hair about once per year. So in 1 year it grew about 8 inches. Now 8 inches, I'm going to convert that into centimeters and then convert it into meters. And 8 inches is about 20 centimeters. So that's about 0.20 meters. And years, I can convert into seconds. And there's a couple of different ways you can do it. But one thing you can do is you can just ask, the internet or ask Siri how many seconds are in a year. Or you can just multiply it out, and I can say I know 1 year is 365 days. And then I can multiply by the number of hours in a day and the number of seconds in an hour. Either way you do it, you end up with the number of seconds in a year of about 86,400. Okay? So the speed at which my hair grows is just equal to a distance, so 0.20 meters divided by a time, 86,400 seconds. And if I compute my final answer and report it in scientific notation, it's 2.3 times 10 to the -6th meters per second, or about 2.3 microns per second. And actually, if you think about what's happening at a cellular level, that's kind of awesome. That is a kind of awesome growth rate. Now, fourth topic, and this is the one that I think bedevils people the most is trig. Now, you've taken math before you had this course, and one of the things you were supposed to have seen was trigonometry. And it turns out basically everything you need to know about trigonometry is covered in Appendix A in the textbook, and the crucial piece of Appendix A is this set of information right here. And you know that the square of the length of the hypotenuse is equal to the sum of the squares of the lengths of the two sides. You know that that's true. You also know something about the sine, cosine, tangent functions. And the way I think about them in physics is that sine and cosine and tangent are just ratios of side lengths of a right triangle. Okay? So I think about them as this. The sine is the far side divided by the hypotenuse, or the opposite side. That's another way you can think about it. The cosine is the adjacent side divided by the hypotenuse. The tangent is the far side divided by the adjacent side, or the opposite side divided by the adjacent. You know that that's true. Okay? And we'll use that a lot. And the reason we'll use it is we're going to do a lot of breaking that into components. And here's an example. So if we look at this particular problem about a black vulture, it's traveling at 9.0 meters per second, and it's gliding at an angle of 5.5 degrees below the horizontal. The question asks this: what are the horizontal and the vertical components of its velocity? Okay? By the way, I want to point something out about this particular problem. This number up here, this 9.0 meters per second, and the 5.5 degrees, that's from a research paper dealing with flight of raptors, okay? And this was data for a European black vulture, and this is a picture of a European black vulture. So the picture matches the data, and the data is real. I didn't just pull a number out of thin air or pull that number out of someplace else. This number is real, and every single number I give you in this class will be absolutely real, and it will be based on real measurements, research papers if I can get them. And the image is a public domain image, so I will tell you where images come from, or else they will be public domain, or else they'll be photos that I have taken personally. But here's how we solve this problem, okay? So I'm going to draw a picture. And I'm going to draw a picture of the flight of a vulture, and velocity we represent as a green arrow, and we're told that it's flying at a 5-degree angle below the horizontal. So if I put axes on, I end up with this. It's a 5.5 degree angle below the horizontal. And I can take that velocity, which is 9.0 meters per second, and I can break it into components. And there's a vertical component, which I'm going to call Vy, that's the y velocity, and there's a horizontal component, which I'm going to call Vx. So we'll see that you can take motion in 2 dimensions and you can break it up into 2 one-dimensional motions. The vulture is gliding at an angle, but we can also think about it as moving horizontally and moving vertically at the same time. So how fast is it moving horizontally? How fast is it covering ground? And how fast is it moving vertically? How fast is it sinking? And the way we do it is this. The y component of the vector is opposite this 5.5 degree angle. So since it's opposite, we use the sine function, and I can say that Vy, the y component, is just equal to that 9.0 meters per second times the sine of the angle, the sine of 5.5 degrees. And if I do that, I get 0.86 meters per second. And you'll notice I've listed this to 2 significant figures because that's how we roll. And that's actually how the data was given to you. It was given to you as 2 sig figs, so you present it as 2 sig figs. Vx is adjacent to the 5.5 degree angle, so we use the cosine function. 9.0 meters per second times the cosine of 5.5 degrees. And that's equal to, basically to 2 significant figures, 9.0 meters per second. It's the same as the actual velocity. So what we did is we took this vector that it was an angle and we componentized it. We turned it into a horizontal and a vertical component, and I did that by using trig functions. And the 2 trig functions I used were sine and cosine. Sine is the one used for the opposite side. Cosine is the one you use for the adjacent side to the angle that you're using. So that's what we need you to know about trig. And if you remember that about trig, you are good to go. Next time, we're going to start talking about motion along a line. And that is the subject that starts being talked about in the chapter 1. But we continue with that in chapter 2. And in the second week of classes, we're going to totally get into chapter 2. That's where we'll start next time. Hope you're having a great day.